haven't seen the slides yet.
Mm.
Oh, here it comes. It was a little delayed, I think.
Okay.
Looks good, Adam.
Looks good. All right.
Oops, my screen froze. There we go.
Looks like we're still viewing your screen, Adam.
I hit stop share.
Okay, I think that's fine now. Thanks. There is a little bit of delay. One thing you could try is, if you have to, you could turn off your video just for bandwidth.
Okay.
Are you going to put Tracy's slide back up?
Sure, Tracy can put it. I don't have it, but Tracy can put it back up. I think we can get started pretty soon. We've got a good group, over 70 folks. All right, well, why don't we get started if you're both ready. So welcome, everyone. Thanks for joining CGD Seminar today. I think we have a few extra participants, so I'll just briefly go over the ground rules for Zoom. Please stay muted during the presentations. We are going to have a transition of presenters today, but we are going to leave the questions to the end. You can either type them in the chat box or use the raise hand feature in the participants window. The seminar is being recorded and it will be available later on the CGD website. And finally, please remember during the discussion to be respectful and share the air. So I'm very happy to introduce both of our seminar speakers today, Clara Desser and Adam Phillips, both of NCAR CGD. Dr. Clara Desser is a senior scientist and head of the climate analysis section here in CGD. She received her bachelor's in Earth and Planetary Sciences from MIT in 1982 and her PhD in atmospheric sciences from the University of Washington in 1989. She served as a research assistant at the Woods Hole Oceanographic Institute, University of Washington, and Ceres, University of Colorado, before joining NCAR in 1997. She is an AGU and AMS Fellow and received the CESM Distinguished Achievement Award in 2016 for her work on the Large Ensemble project. Clara's research interests include global climate variability and change in observations and models, role of internal variability in regional climate change, and decadal climate variability. Our second speaker is Adam Phillips. He is an associate scientist 4, also in the climate analysis section of CGD. He received his bachelor's in atmospheric science from the University of Missouri in 1997 and his master's in atmospheric science from the University of Illinois in 1999. He joined NCAR in 2000 and has worked on scientific analysis, programming, web development, and support for NCL and CESM. He has also worked extensively on developing diagnostics packages, and he received a CGD Special Recognition Award for the development of the Climate Variability Diagnostics package in 2015. So relatedly, today, Clara and Adam will discuss the NCAR Climate Variability Diagnostics package for large ensembles. And I think Clara is going to get us started. Go ahead.
Good morning, everybody. Katie, can you see my screen?
Yeah, it looks good.
Good. All right. Well, thank you so much. And thank you so many people joining today. And having an interest in this new diagnostics package. It gives me great pleasure to finally be able to present it to everyone. So Adam and I will share the air today. I'll go first, and then Adam will take the middle part of the talk, and then I will wrap it up at the end. So this project has been kind of a long time coming, and we're really happy that it's at a stage where we hope it'll be of value to many of you. And it was done in collaboration with other members of the climate analysis section, including John Fasulo, Isla Simpson, and Dave Schneider. So as Katie mentioned, Adam got an award for the original Climate Variability Diagnostics package. And this new one builds on that, but it is specifically tailored to large ensembles, and you'll see that as we go along. So like the original CVDP, as we call it, this is an automated analysis tool and data repository for exploring forced and internal components of climate variability and change. And I want to emphasize the word exploring. This is a tool that has inspired a lot of my own research, but it is not a black box, and you don't get Journal of Climate papers by just applying the package. You have to, you know, think and just have fun exploring the data. So really the spirit of the package, like the original one, is to sort of make one think and think of questions and hypotheses that come to mind as one looks at the output from this package. So for example, some of the questions that could be addressed by applying this package: how well does my model, whatever model that is, simulate, for example, ENSO, Atlantic multi-decadal variability, Pacific decadal variability, Atlantic meridional overturning circulation, NAO, variability in general. That's really what this package is aimed at. And then one can also address how does my model compare with other models? And in fact, are there true structural differences amongst models, or are they only apparent differences that arise because of limited sampling of internal variability? Another question that can be addressed, does climate change affect the characteristics of internal variability? And also on the flip side, how does internal variability contribute along with forced climate change to long-term trends? So these are just some of the kinds of questions that one can address with initial condition large ensembles and with this package in particular. So I thought I'd just give a very brief introduction to initial condition large ensembles. I'm sure all of you probably know, but I thought it's nice to put us all on the same page. And I would also point you to this paper that was recently published by the US CLIBAR Working Group on Large Ensembles. And this really goes through a lot of aspects of how they are useful, what are they, how large do they need to be, how are they best designed, and what are some of the emerging applications and future directions for initial condition large ensembles. So I thought just helpful to see schematically how large ensembles are designed. And I'll use the example of the CSM1 large ensemble project that is written up in the K et al. 2015 article. So for this particular large ensemble, we began with a long control run under 1850 radiative forcing conditions. And then at year 401, we hit the system with a hammer. That is, we hit it with the external radiative forcing protocols, historical and RCP 8.5, that was used in the last IPCC assessment. And that first simulation then ran all the way to 2100. And then in 1920, we decided to launch a whole ensemble of additional simulations. And the only difference amongst them is the initial condition in the atmosphere in the year on January 1st of 1920. And this perturbation was very small, on the order of 10 to the minus 14 degrees Kelvin, truly the butterfly effect. And then that leads to sort of 40 parallel worlds that could have occurred, according to this model, under the combined effects of the externally imposed radiative forcing and this internal climate variability that goes along with the different sequence in each one of these members. And the important aspect is to note that beyond the typical predictability timescales that we know about in the atmosphere and the ocean, typically the spread amongst the individual ensemble members is not predictable beyond roughly a decade. You know, it depends, of course, on what quantity exactly you're looking at. So large ensembles, initial condition large ensembles, have now really blossomed in the community. And one of the activities of the CLIVAR working group on large ensembles was to put together an archive of some of the fields from 7 of the CMIP-5 models that did run large ensembles. And Flavio Lehner in particular did a lot of work to put together a data archive that can be accessed by anybody by going to this website. And we hope that this has made it easier and facilitates multi-model comparisons across CMIP, large ensembles. And then we also show in this webpage the large ensembles that we are aware of to date with CMIP-6 models. And there are roughly 10 models that have ensembles of at least 10 members that we decided was adequate to include here. So like the original package, this one also computes modes of variability, trends, and various regional and global climate indices. All the output is saved to a data repository, so you can analyze it further at a later time. And everything is up to the user. You can decide what models, what observations, what time periods you want to analyze. So what is new for the package that is for large ensembles? Here we have, in addition, we have also computed ensemble mean statistics and ensemble spread statistics. And I'll show you that as we go along. I think they're very insightful. And then we've made an effort to be more quantitative in our comparison with observations, and in particular using some rank metrics, as you'll see during the talk. And then finally, we've written up a comprehensive user's guide. This user's guide is 35 pages. Luckily, it is, you can search for different parts of it, so you can jump around. But we really wanted to make it informative, not only as a tutorial on the package, but also as a helpful, maybe standalone or self-contained teaching resource for graduate students who are making use of large ensembles and want to know sort of background on internal variability, the utility of large ensembles, and then getting into a fully referenced set of diagnostics that the package contains and computes, and metrics, how observational uncertainty, very important, how that is treated in the package, how to interpret the plots and the metrics that are shown in both the ensemble summary view and the individual member view. And then finally, sort of a discussion of perhaps best practices and suggestions or ideas for how one might creatively apply the package. This is now the user's guide, has a DOI, and you can access it via the website for the package, and hope you find that useful. So before turning it over to Adam, I'm going to just give you an overview of what the web page looks like once you run the package or once you access some of the comparisons that we've already run and that are in the data repository. So for those of you that know the original climate variability diagnostics package, this on the face of it looks very similar. So I'll just walk you through some of the elements. So there's always going to be a title, and that is up to the user to specify. In this case, I'll show you some results from the CMIP5 multi-model large ensemble archive, the analysis for the time period 1950 to 2018. So the user gets to put that title of their comparison. Then there's a link to the user's guide. There are two ways, as I will describe in detail, of viewing the output: the ensemble summary view and the individual member view. Then we have a lot of summary metrics that can be viewed both in graphical and tabular format. We are analyzing 5 different variables: SST, surface air temperature, sea level pressure, precipitation, and sea ice concentration in the northern and southern hemispheres. And all plots and diagnostics and metrics are available for the 6 seasons and the annual mean. So just show you all of an overview of what we compute in the package. So in the green circles, you can see we have maps of climatologies. We have maps of interannual standard deviations, and we have maps, global trend maps, so trends portrayed in the global format. Then the meat of the package, I would say, is devoted to these coupled modes of variability. ENSO takes up about half of it, and we have lots of metrics on El Nino, La Nina, their difference, and a lot of aspects of the Nino 3.4 SST time series. We also have AMV and PDV and AMOC. Then we have 8 different atmospheric modes of variability. These are selected as the leading modes in the 2 hemispheres as well as the tropics. And you get both the patterns and the time series for each one of these. And then we have global time series for the different variables, and a bunch of regional time series that you can see here. Hopefully your favorite one is on it. And then finally, we devote a whole section to sea ice extent. And there are a bunch of different quantities, different ways of viewing sea ice. So that, in a nutshell, are all the different diagnostics that are computed. And now I'm going to hand it over to Adam to give us an overview of the development process, technical guidance, and a description of the web page itself and the data repository. And then Adam will hand it back to me, and I'll give you tutorial, if you will, on how to interpret what is on the plots and the metrics, and then hopefully pique your interest by showing you results that are applied to both the CMIP5 and CMIP6 large ensemble archives. So with that, I'm going to stop sharing, and hopefully, Adam, you can put up your slides.
Okay, can you see my screen?
No, not yet. Oh, there it is. Yep.
Okay. All right. Well, thanks, Clara. So I thought it important to just briefly go over the path that we went down in developing this package. We started working on this back in February of 2019, and we had hoped to release a version by the end of that year, and that very much didn't happen, as you can tell. And there's a few reasons for it. One of which we ended up putting a lot more metrics in the package than I think we originally thought. The reason is it was not able to code continuously for those 20 months. There was a lot of fits and starts. where I'd stop for a month or two and then come back to it. There's a few minor ones, but one big reason why it took longer at the very end here is that we tried very much to keep ease of use in mind as we were developing this package. And so what do I mean by that? I mean, we wanted to make this package so that not only is it easy to run, but it's easy to analyze the output, that there's a consistency amongst the plots. Everything is very clean, it's well documented. And through that lens, a lot of the different things, different aspects and asks that were made is how do we make this so that it's as easy looking at the graphics, or you're reading in the netcdf files of the package that the package outputs, how to make that as easy for folks to use as possible. I'm not going to read through this list, but a lot of these can be viewed in through that lens of, all right, so and how do you, does the user have to worry about what grid the input data sets runs? They don't. For the most part, they really don't. The titles are always, they don't run into one another. Everything's clean. And so we tried to make this package so that from the beginning to the end, it makes it easy for folks to use. And I believe that that's important, because if you make something that's easy to use, folks will use it. And if you don't, they won't. So yeah, so that is one over something that I kept in mind. There are over 28,000 lines of code. The CVDP-LE will produce around 1,000 plots, which is triple the number that the CVDP creates. That's if you run the package to its fullest extent. You have the option of saying, hey, I'm just interested in a specific metric, so let's just calculate that, don't run the full package. So if you're interested in, say, the Southern Oscillation, you just want the pattern and time series, you could tell it, just run that, and that will reduce the time spent for the package to run. Clara already alluded to the new user's guide, and that's great. We also have a new website and we've created a new readme file to help people run the package. So some timings. So is this because the CVDP-LE creates more plots, there's more output, it does take a little bit longer to run in some instances, but where we've seen a great improvement is for large comparisons. So if you were to feed in 384 115-year runs from the CMIP6 historical archive, that comparison took me 18 hours this past weekend. Now that's running with parallelization turned on. So I employ simple parallelization through Python to call a number of scripts at once, and that number is set by the user via options. And 5 or 6 seem to work best for me. But we've seen a great improvement for the larger comparisons. If I were to run that same comparison through the CVDP, it could potentially take days. So that's where we've seen improvement in timing. For smaller comparison, like a 10-member, it will take you coded in NCL. And the answer to the rhetorical question is yes, NCL was developed in the 1990s. So why was that used here? Well, there's a few reasons. The first one is just practical. I know NCL very well. I don't know Python that well yet. And we had a time limit in that we wanted to get this package out within a few years. But probably the most important reason is that even though NCL has been feature frozen, for those of you that don't know, NCAR Sizzle staff that are the stewards of the NCL project have frozen the package. They're not going to put in any more features that have been added by developers. They're going to still add user contributed features, still just allow distribution, do builds, and do support for installation and such, but they're not going to be adding anything to the language itself. They've moved on to developing more Python-based tools. But for that being said, after discussions with them and just knowing how many large projects are still using NCL around the world, I have confidence that NCL will still be able to be used 5 years from now. So for example, large projects, IPCC figures, you could still submit them in NCL. The ESM Val tool effort, which is a collection of diagnostics packages that they took from centers around the world and are brought under one umbrella to analyze the CMIP6 archive. NCL is one of the 4 languages that can still you could submit metric diagnostics in along with Python, Julia, and R. So there's examples both big and small of NCL still being used, and I do have confidence that that will continue to be the case years into the future. Now, if this package was to be created from scratch and we weren't starting with the CVDP code base, which was an NCL, we probably would not have done it in NCL, we would have used Python. All right, so a few more coding improvements and additions that are different from the CVDP. So the model file identification section of the coding has been completely rewritten, and that's important because over the last year I've received more reports of the CVDP file identification section failing due to an increasing number of variables that are present in CSM2, as well as different directory structures that are being used nowadays. So I've rewritten that. It's much better. I haven't been able to break it, although I'm sure somebody will find a way in the future to do so. So that has been rewritten. Clara mentioned it calculates ensemble graphics metrics, but it also computes differences from observations, and that's a big difference from the CVDP. A few other items. It now has the capability to be run in data-only mode. If you're only interested in metrics, don't care about the graphics that the package provides, you can just turn on data-only mode. It'll compute the metrics, write the netcdf files, and it'll stop. So that is a time saver. As I mentioned in my research report 1.5 years ago, the code, I wanted to make the code much more modularized than it is in the CVDP, and I believe I've done that. The calculations are, for the most part, completely separated out from the graphics, which allowed me to easily put in data-only mode. And the modularity really makes it easier to strip out sections of code to use for outside applications or individual research. For example, the package calculates a number of EOFs. Just for the atmospheric modes, for instance. And there is one line that you just pass in the array, the area that you want to analyze, and the number of EOFs that you want to calculate. And it'll return EOF patterns for 7 seasons, the significance of those patterns, along with the associated principal component time series, so just one line. So it's examples like that that have been put into the CVDP LE, and I think it'll help not just making the code easier to maintain and stuff, but it makes it easier for people to strip out parts of the code used in their own applications. Finally, the package will read in previously created metrics. So if you have previously run this on a 10-member ensemble and then another 5 members are run, the package will realize, oh, it's been run on the first 10 members. It won't recalculate those metrics. It will just read them in, and then it'll calculate the metrics for the final 5 members and stuff. So that is another big time saver. All right, so how easy is it to run? We think it's very easy. It's exceptionally similar to the CVDP. Similar again is that there are 3 things that you need to set up. You need to set options via the driver script. You need to tell the package where the simulations are that you're going to analyze, and you need to tell the package what observations you want to compare against, if any. So just quickly running through that. Oh, before I do that, you do need to have NCL, Python, and ImageMagick installed on your systems. And it only analyzes monthly CSM or CMIP time series files. It has the capability to read in monthly time series files from any modeling center, and I have written directions on how to do that. It does not read in daily data, and it does not read in CSM history files. Okay, so getting back to the 3 things you need to set up. So this is the top half of the driver.ncl script. It is an NCL. You don't need to know NCL to set these options. So this is showing a subset of the options. There's a total of 16, of which most people who run the package will set all of 4. And you can see how well documented each option is. So it's pretty clear on what you need to do to set things up. Once you set those options up, you can move on to the name list. And the name list is, this is the one change from the CVDP. So there are now 5 columns of information that you have to enter for each run. So the run name, which can be whatever you want in that first column. The second column, so everything's separated, as you can see by the vertical bars. The second column is just the generic path to where the data lies. The third and fourth columns are the start and end year of analysis, not the start and end year of the data set. And then the 5th column is the identifier of which ensemble each one of these runs you want it to be a part of. And so that's the new part from the CVDP. So there are no restrictions, there are no restrictions on the number of models you list. The ensemble sizes can be different. You can analyze different years between different ensembles and such. But one thing that I wanted to highlight as well is that you could highlight the exact same simulation multiple times. So in one of the comparisons that we ran, we took the 2000-year CSM2 pre-industrial control run and split it into 2100-year segments. So you could treat it as 20 ensemble members. And then the package will say, all right, so those 20 members are part of the same ensemble, and you'll get ensemble metrics based on that. And then I did the same thing for the CSM1 large ensemble pre-industrial control, and had 18 100-year segments, and I'll show a brief result of that in a bit. Nameless OBS is the exact same thing as what we had set up for the CVDP. You're specifying for each of the 7 variables that the CVDP LE reads in, you're specifying what observational data set you want it to analyze. And you could have as many observational data sets per variable as you would like, or you could have just, you could have no observations other than a single SST data set. It doesn't really matter. It's flexible. All right, so it's very easy to submit the package. It's just like other NCL, calling NCL, you say NCL driver.ncl once everything is set up. You could run on any machine that has the before mentioned software stacks installed. And I've been running it regularly on CGD and Sizzle on Casper on those machines. And it runs very well. So it's pretty easy to get up and get going. But let's say you don't want to run the package, you just want to look at the outputs. So we have, as I said, a new website. And on so this is a screenshot of the homepage. And if you wanted to look at what we have comparison-wise to look at, you can click on the data repository on the right-hand side, the navigation bar on the right-hand side. And once you go to that data repository, it'll take you to a listing of what comparisons we've done. And so for each, so what we've done so far is we have 3 comparisons for the MMLEA archive over different time periods. We have a comparison for the CMIP6 historical scenario from 1900 to 2014. And then we have the before mentioned CSM1 and 2 controls where I split them out into 100-year segments. For each of those, you have the option to click on images, which will just show you the graphical metrics, or data. And if you click on data, you'll get a tarball that contains netcdf files, 1 for each run that was analyzed, and then 1 for each ensemble mean that was created. And then each of those files has each of the metrics that we have calculated in them. So you can go and read in the Nino 3-4 time series for each of the 384 CMIP6 historical scenario runs and stuff. So you don't have to download the entire archive. You can just download the comparison that we did here if we did what you needed. Okay, so just a few selected graphics that I find very interesting. So as Clara alluded to, there's different types of metrics or graphics to look at. You have the ensemble summary view, you have the ensemble metrics graphics, of which these 2 are a subset of, and you have the individual members view. So this is the ensemble. This is 2 metrics from the ensemble summary. I'm sorry, ensemble metrics. Clara will show you the full set of metrics later on. And so what this is showing, it's just showing the pattern correlations computed between maps for each model run. You compute the SST standard deviation for annual, and then you do that for observations, and then you compute the pattern correlation between model A and the observations, and then that's represented by a line on this graph. Then you do that for every model, and then you group them by ensemble, by which ensemble they belong to. And then that's it. And then the panel on the right-hand side shows the exact same thing except for precipitation over land. And these are just 2 that I picked out, and CSM2 in these metrics look pretty good. Now I could obviously show you where CSM2 doesn't look as good, but in these 2 metrics, CSM2 stands out above the other modeling centers in how well it represents a variability in the SST and precipitation fields. So no CVDP or CVDP-LE talk would be complete without showing an overwhelming number of postage stamp plots. And so that's what I did here. There will be a quiz on the 204th member later on. But anyway, jokes aside, you can see that there's a blank plot in the middle. And so the 2 things I wanted to highlight here. One is that the package does not care if there's something wrong with the data, or the data is missing, or the data doesn't completely go through the range of years that you asked it to analyze for a specific member. The package will just leave a blank plot. So that's what's happening there with the blank plot in the middle. But the other thing I wanted to show is that even though there's an overwhelming number of panels here, that you can zoom in and see details of a specific panel if you need to do so. So it doesn't have to be so overwhelming. All right, finally, So going back to what I referenced, that CSM 2 and 1 control, where I split things by 100-year segments. So this is now looking at the individual members view of that. So it's showing the Nino 3-4 power spectra for each individual 100-year segment, 5 selected ones for CSM 2 on the top row, and for CSM 1's control in the bottom row. And you can see the top row, the titles are in blue. The package, the CVD-PLE will identify which member, which ensemble each member is a part of, and will color the panels accordingly. So CSM2 in this comparison is blue, CSM1 is green. So now I'm going to shift from the individual members view to the ensemble summary view of this metric, and just focusing in on the top plot. So the dark blue line is just the ensemble average of the 20 100-year segments from the CSM2 control. So that's the ensemble mean in dark blue. The light blue shading shows the range, and Clara will speak more to that a little bit later. Then I do the same thing for CSM1 down below. And then there's a third panel that shows the ensemble means in blue, corresponding to the title color, showing CSM2, and then the ensemble mean for CSM1 in green. And then it also shows the power spectra for observations on the same plot. So you will get a summary plot that just sort of synthesizes everything for that specific metric. So the code is now available on CGD and CISL systems. It will be available on GitHub by the end of the week. I just created a GitHub page this morning, and I'll be adding to that over. So I'm hoping that I'll get that up within the next 24 hours. So before I turn it back to Clara, I just wanted to thank everyone who has sent in comments and suggestions over the last 6 years with regards to the CVDP and CVDP-LE. We very much appreciate it. And the comments are what turned the package into what it is today. So thank you all. So Clara, I will turn it back to you.
Okay, thanks, Adam. It's an amazing tour de force that Adam has put together, I really have to say. So now I'll just give you some information about how you interpret the plots and the metrics, and then wrap it up. Whoops. So as we've already alluded to, there are sort of 3 doorways that you can enter to look at the output. There's the individual members view. I'm not going to show you that at all. It's the same as what you get in the CVDP by and large. Then there's the ensemble summary door and the metrics door. So we'll start with the ensemble summary door, and I'm going to show you spatial patterns, how you look at those, and then time series and quantities that are derived from the time series. So for my spatial pattern example, I'm going to pick the NAO in December, January, February, so the northern winter seasonal mean. And what I'm going to show you, you will get the same plots and information for all of the other metrics that are computed in the package. So everything I say here carries over to any other spatial plot. So if you just, I'm just blowing up sort of the first row of plots that you might get when you apply the package. So here in this case, you'll get 4 columns. You'll get the model, the observations, the difference between them, and what I call the observational rank. And I'll tell you what that means in a moment. So you'll get all the information you need, the model name, the number of members that you have decided to include in your analysis, and the time period of analysis. And they do not have to match between observations and models. You can use a control run. You know, they can be different, and it of course depends on what your application is. So the EOF, the user's guide, will tell you exactly how that EOF is computed. In this case, it's within that triangular region of the North Atlantic and Western Europe. And importantly, this EOF is computed for every individual simulation of a particular model's large ensemble. And that's shown in the individual members view. And then here for the ensemble summary view, we simply average those maps. and show you the average across all the members. So the EOF is computed within that triangular domain. Then we have the PC time series. We normalize that by the standard deviation, and then we regress the original sea level pressure field at all the grid points over the northern hemisphere onto that PC time series to get this hemispheric expression of the NAO. So I'll show you what is probably invisible on your screen here. But what you see here circled in green is the percent variance explained, the distribution of that across the ensemble. So we choose the 10th percentile ensemble member, the 50th, and the 90th percentile. So for the case of the CCCMA model, the range of variance explained goes from 42% to 53%. And those are just plausible given the model's internal variability and forced response. And then you can see the observations for this particular comparison. It explains 47%. So this model just happens to be centered pretty much on the observational value. Then you also get the pattern correlation between this ensemble summary map and the observations. And in this case, the pattern correlation is 0.89. So it's a really excellent depiction of the spatial pattern of the NAO. However, of course, you can see differences between the model and the observations. That's shown in the difference map. And in particular, you really see the North Pacific coming out as having a big difference between the model and the observations. So to provide a little bit more insight into, rather than show statistical significance, we've decided to add a separate panel that shows the observational rank, meaning where, if you sort all the ensemble members of the model, and where does the observed value lie? And so this just shows you a map of that. So white areas are showing you where the single observed value lies within the 20 to 80th percentile spread of the model, i.e. the model is very realistic. And then the green and blue areas are showing you where the observations lies within the tail of the model distribution or even outside. So the darkest blue means that the observed value is less than the value that you obtained in any single member, i.e. it's a real model bias. And the dark green is on the other side where the observations are larger than any single member. So for example, the North Pacific, that difference is clearly a model bias. No ensemble member at all overlaps with the observations. And even within the sort of NAO region itself, although the difference map may be a little bit more subtle, it actually is a true model bias because the observations really lie outside the model distribution. And then finally, we show you in the upper right-hand corner of the rank plot, the area of the area covered by ranks between observational ranks falling within the 10th to 90th percentile of the model spread. And in this case, it's 36%. So that's maybe a helpful metric to decide, how well the model does in the pattern. So now let me move on to what I think is the beauty of the package, which is that you can run it on whatever multi-model collection of large ensembles that you're interested in and really get a very informed view of model intercomparison. So what I'll show you here are these 7 CMIP5 large ensemble archive models contained within that archive. And I'm just showing you the number of members that each one of them has. Of course, they're all different, which is why we purposefully chose our rank statistics to be in terms of percentiles rather than absolute number, the absolute number of simulations. So here's the postage stamp maps. And of course, they're all small, but as you look at these, you can really see very, I think, informative, and especially in terms of this rank plot. If you just have your eye focus on which models have more white space versus blues and greens, and very quickly you can really come to see that in this comparison, the MPI model is the most realistic for the NAO. It has the largest areal coverage, 60% of observations falling within this 10th to 90th percentile ensemble spread. Now, of course, if a model has much too large variability, it might be very easy for the observations to lie within the model spread, but that doesn't mean the model is realistic. So you really need to check that the amplitude of the internal variability in general is realistically simulated in the model. And for that, you can simply go to the standard deviation maps and compare observations and model to see if the model is credible in terms of its ensemble spread. So now let me just show you analogous types of plots in the time domain. So first I'll show you time series. So again, I'm picking out one example. The case here is global mean air temperature, but any of the time series in the package have the same information on them. So you get a lot of information. You get the observed time series in gray. The thin dark blue line is the ensemble mean of the large ensemble. And then you get ensemble spread, the light blue being the 25th to 75th percentile spread, and the darker blue being the 10th, or I misspoke, it's the other way around. But the 10th to 90th would be then the light blue. But I think you see what I mean. So then you get, of course, the model name, the number of members, color-coded, and you get the observational name and time period that you've chosen to compare the model to. And then you get information on the linear trend from the observations, and you get information on the linear trend for the time period shown in terms of the distribution across your ensemble. So you get the 10th percentile value, the 50th, and the 90th percentile value. And then these percentages that are shown at the lower left of each panel is a percentage of time that the observations fall within the 10th to 90th percentile model spread. So it's very analogous to what we did on the spatial maps, but now this is in the time domain. And you can see there's a large spread. CCCMA, it only falls within 45% of the time, encompassing the observations, and MPI, 87% of the time contains the observations. So that's a very informative metric. I do want to point out that on purpose, we have not tried to hardwire a single y-axis range, because the models really vary and it would compromise sort of viewing the information for each model if we tried to hardwire a single range. And so for that reason, we include at the bottom an ensemble means summary map where we just show the ensemble means from all the models on a single plot so you can compare their amplitudes. And they're color-coded by model according to how these model names are color-coded. And then again, just reiterating, all of these numbers, time series, ensemble spreads, you get all of these saved to the data repository. So some examples of derived quantities from the time series. I thought this was a fun one to show. The lag autocorrelation curves for the Nino 3.4 SST index after detrending. And this is applied to the CMIP6 historical simulations, large ensembles. And the first thing is you can really now be very quantitative about how your model, which includes internal variability, how that compares with the single observational record. Does it encompass the observations? Are the observations fully outside of the ensemble spread? And then the ensemble means summary, which I've blown up here on the right. I think it's very just apparent that there are different classes of models, and some of them have a shorter negative autocorrelation time scale than others. And that's something that is just immediate when you get these kinds of plots. And then my last example for a derived quantity is coming back to the power spectra for the Nino 3.4 SST index. This is for the 16 CMIP6 large ensembles. And again, just a real variety of amplitudes and time scales and spectral peaks. So I think it's quite informative. So now I'm just going to wrap up in the last 2 minutes here and then make sure we have time for questions. We will look through the metrics door. This is one of my favorite. So I just want to show you some of the types of plots that you get. So first we'll look at the graphics and then at the tables. And Adam has already given us a preview of the graphics, but I just want to go through it in a little more detail. So here I'm just going back to the original example of the wintertime NAO. You see the map there in the upper right-hand corner, and I'm going to be looking at the CMIP5 multi-model large ensemble archive. And what you see for each large ensemble, you see on the left, the pattern correlation for each member, its NAO representation, and the observations that you have chosen to compare against. So that's on the left. And then on the right, we complement the pattern correlation with a spatial RMS difference. So that's giving you quantitative information on the amplitude, the realism of the amplitude of the NAO pattern. So the first thing is importantly to treat observational uncertainty. So as Adam mentioned, you can decide to compare against a whole bunch of observations, and you can choose to vary the data set and the time period and or both. So here we've picked out some examples where we varied the data set and also the time period. And then we do the same pattern correlation against our reference observations, which in this case is the ERA 20C from 1950 to 2018. So that gives you very useful information on the observational uncertainty to begin with in this metric. And then you can compare the models and sort of benchmark them also against that observational uncertainty. So in each one of these comparisons, we also highlight with a sort of longer fuzzy bar the 10th, 50th, and 90th percentiles of these pattern correlations and the spatial RMS difference. And I think that's extremely valuable. So I've highlighted here with the black boxes the CSIRO model and the MPI model. And for this comparison, the 90th percentile, so sort of, at the top of the distribution of the best simulations from CSIRO, they are, the 90th percentile lies below the 10th percentile of the MPI. So you can really say with some confidence that the models really are structurally different in their depictions of the NAO. And this point has been made also in a recent paper led by John Fasullo. So it's not simply that you happen to sample a different sequence of internal variability in your model simulation compared to the observations or between the models. It really is robust to uncertainty due to internal variability. And you can also look at the amplitude in terms of the spatial RMS difference. And the same thing holds that the 10th percentile of CSIRO has a bigger spatial RMS bias than the 90th percentile member from the MPI. So really structural differences between models. And this, I think, is sort of encapsulates what I think of as sort of a hallmark of the package, that it can pull apart model differences that are due to that are only apparent because they're actually due to different sampling of internal variability versus true structural differences that transcend the uncertainty due to limited sampling of internal variability. And now just for fun, what does the winter NAO look like in all of the CMIP6 models, and you get just beautiful, very informative graphs. But I'm just highlighting down at the bottom here in the green, all the models do really well. Pattern correlations exceeding 0.8. So they're doing really well, but there is a large spread. And just to make the point that just because a model might have a low pattern correlation sort of distribution, that doesn't mean it has, the worst. It's the worst in terms of the amplitude. So that's just something to pay attention to. Okay, so we've done these sorts of plots for 11 sort of judiciously chosen metrics. But of course, we're not trying to be totally objective here. And we've heavily weighted our metrics towards ENSO and then other leading modes of variability in the system, as you see here. And then we've computed a mean score. So we suitably transform these correlations with a Fisher Z transformation, I believe, and then come up with a mean score across these metrics for the models. And that is as just what I said before. You can finally, really determine if the models are structurally different in these modes of internal variability, or whether their differences are just within the noise of the uncertainty due to internal variability. And CSM2 performs amongst the top performing models. And then the tables, you get the same information in beautiful color-coded tables that you can sort according to whatever metric. I won't go into it, but I hope you have fun doing that. And you get all of these saved to the data repository. So you can make your own plots of these numbers if you wish. And this is available, of course, for every member of every model. And then the user's guide, we just give a few suggestions on fun ways to apply the package. For example, you could use multiple time periods in a single application to see if the modes of variability are affected by climate change. Do they change with time? You can use it on subsets of ensemble members to see how robust your results are. You could filter the data, low pass filter, for example, or high pass filter, to investigate the dependence of the modes of variability on time scale. And of course, you can use shorter segments of a long control simulation to assess control runs. So with that, I very much thank you for listening. And Adam and I are very happy to take your questions and, of course, continue any dialogue via email after the end of the seminar. Thank you so much.
Thanks, Clara and Adam, for a great summary. Yeah, I want to echo Judith's comment in the chat that this is a really great package, and I know it's going to be very useful for the community. So a couple of questions came in the chat, but I believe they were addressed by Clara's last section there. If they weren't, or if there's follow-up, feel free to type additional questions or use the raise your hand feature in the participants window. I'll also note that Adam provided some links to examples of applying the package, and so you can go and check those out. Looks like we have a question from Bill Large. Go ahead.
Yeah, the package is fantastic, but my question, just because I'm interested, is are there formal communication channels that you've set up between that users can talk to each other, or you with bulletin boards, or perhaps contribute software or different things, or where are you on that kind of moving ahead?
I'll let Adam answer it, and I think the answer is by and large, yes. Go ahead, Adam.
Yeah, I mean, so we ask that folks, if they have questions, that they post to the CSM bulletin board, following what we do for other, but so that's for questions and stuff, but they're always, we're very much welcome folks to just email us. So we have our information on the website under support and contact us on the navigation side of the page. And that provides our email addresses so they can contact us. We don't have anything more formal than that yet, but I think we're definitely willing to consider it.
And I would be happy, we're always happy to entertain suggestions for adding diagnostics or metrics, as long as, the package doesn't slow down too much by having too many, but we want to make it useful to everybody. That's why we did this. So we very much welcome your ideas. And I would also go beyond that and say that we would offer to run comparisons that you would like. Again, this is just in service of getting the community to really look at large ensembles and compare them between models. But thanks for your question, Bill.
Other questions? Clara, I was curious about the effect of ensemble size. I mean, you talked about how MPI was the most realistic in certain analyses, but it also seemed to be the most largest by far of ensembles. Did you have ways of accounting for that, or ways of looking at that?
Well, I think that is something to be explored, and I think that's I was trying to allude to that. I think in my ideas for how to apply the package effectively. And I think rerunning the MPI with, let's say, 30-member subsets, and then using that same ensemble size for the other models, that could help you address that question. Again, we try to use these percentile statistics to kind of mitigate a bit against differences in ensemble size. But it is a very important point, and maybe, with 70 members, your spread, well, I don't know. I'm going to be careful what I say, whether it becomes larger, but certainly by 70 members, you've sort of probably sampled, most of the distribution. But yeah, that's something that one has to really think about when applying the package.
See a question in the chat from Anna. Does the package require global spatial scales?
You mean, does it have to be run on global data? I'll let Adam answer that question.
Yeah, I'm assuming that's what the question is about, but Anna, feel free to unmute and clarify.
Adam, the answer is yes to that?
Yeah, sorry, I was waiting to see if Anna wanted to say something. The answer is yes for the atmospheric variables. The sea ice variables, no, they do not have to be. And then MOC, of course, is not global. But for the atmospheric variables, yes, it does assume that it is getting input for global input.
Okay, another question from How Fan in the chat. The models on MMLEA don't all have the same variables available. Is that work in progress?
So that is work led by the US CLIVR Working Group on Large Ensembles. And this was sort of put together about 1.5 years ago to really get the data into people's hands, because we found that's sort of the biggest roadblock to analyzing and comparing different models, large ensembles, is just downloading the data. So Flavio, it just took a lot of work to contact each modeling center, find a contact person, and get the data for a limited set of fields. And not all of the modeling centers were able to get us all the different fields that this package operates on. I'm sort of going to leave it a little bit open-ended whether we are going to complete the full set of variables from all the models in the MMLEA. I think that's sort of a little bit more in Flavio's purview, and I don't want to promise too much. But you can, of course, get these data from the CMIP5 archive and, of course, CMIP6 archive. But this MMLEA was just an initial attempt to give you, sort of the best we could for the collection of variables that are used in this package.
Great. Lots of additional thanks and acknowledgements in the chat. A suggestion from Christian to consider QBO metrics. And then I saw Rohini had a hand raised, so go ahead.
Can I just answer the QBO one? Because we get asked that a lot. QBO,
Sure.
MJO, I agree. Those are incredibly important modes of internal variability that we really want to, scrutinize our models for. We made the conscious choice to limit this package to monthly input data. But that said, I think there's another effort that people here in CGD are part of that is going to build a package or is already in that stage for more sort of intra-seasonal modes of variability. And we are more than happy to provide the coding. Adam can offer his expertise on how one might include some of these diagnostics that we have in this package that could be then entrained into a package that would be for daily data. But I think it would slow this package down a lot if we started to then open it up to the daily data.
Okay, great. Thanks for clarifying that. Rohini, go ahead.
Yeah, thanks a lot and great package. Once again, thanks for making this available to the community. It goes to somehow like Anna question and the Adam that answered about the atmospheric variable. Cannot we trick the code by giving, of course, the all global data, but filling up with missing values, and just in the regional statistics where we are like interested, just give that value. So this fills the requirement of input, but still doing a regional statistics.
Yeah, that's a great point. And we had previously gotten comments over the years that, hey, it'd be great if we could run WRF through this, or that just has regional output. But that suggestion is a good one. I had not considered that. The reason the package will fail right now is if you pass in, if you pass in regional output, is that it'll compute the EOF for the NAO over the North Atlantic. So if that region's not there, it's going to go just the way that I've coded it up. But that is a very good suggestion. I will definitely consider that for future releases.
Thanks.
Okay, we're a bit over time, but I think we'll take this last question in the chat about this package and how it possibly relates to ESM Val tool, if either of you have comments on that.
Yeah, thank you for that question. So the CVDP, the original package, is in ESM Val tool, and it has been from its inception, or the inception of ESM Val tool, that is. So I just emailed yesterday Veronica Eyring to let her know about this new package, and would be delighted if it were included in ESM Val tool when the time comes. And I'm certainly hopeful that it will. And I think that would be a great way to get it out into the community. Thanks.
Okay, great. Well, I don't see any more questions. So thank you both very much for a great talk and a great discussion. Next week is actually our last CGD seminar of 2020, and we will hear from Dan Witt, also of NCAR CGD. So hope to see you then. Thanks again, Clara and Adam.
Thank you. Bye-bye.